While historians obsess over Arkwright's mills and Bolton and Watt's Soho manufactory, there existed an entire parallel universe of mechanical innovation that never made it into patent records. We're talking about workshops that appeared in no registry, employed no official apprentices, and left almost no paper trail. Yet they were everywhere. Picture this. In the 1780s, Manchester alone had perhaps 30 documented machine shops, but tucked into cellars beneath cobbler stores, in converted stables behind alehouses, and in what appeared to be ordinary blacksmith forges, there were at least twice that many operating in what we might call technical twilight. These weren't just repair shops. They were reverse engineering laboratories. Here's what's rarely discussed. The major factories had a catastrophic problem. Their machines broke constantly, and the manufacturers who held the patents couldn't service them fast enough. A water frame with a snapped spindle could sit idle for 6 weeks waiting for an official repair. So factory owners, desperate to keep production running, quietly hired unaffiliated mechanics to fix things right now. These mechanics couldn't just patch. They had to understand the entire mechanism, often improving it in the process. The economic incentive was irresistible. An official replacement gear from Bolton and Watt cost £3 and took 2 months. A skilled copyist in a cellar workshop could produce the same component for 15 shillings in 3 days. The quality, often superior, because these craftsmen weren't working from blueprints. They were working from the actual broken piece in front of them, learning from every fracture point and wear pattern. What's fascinating is how these workshops functioned as knowledge networks. A millwright in Leeds would accidentally leave a damaged pumping engine component at a certain Manchester tavern. 3 days later, he'd return to find it repaired, improved, and accompanied by a hand-drawn sketch showing the modification. No names, no receipts, just the work. The silence wasn't romantic. It was legally necessary survival. Between 1760 and 1800, Britain's patent system was a minefield. If you improved someone else's machine, even accidentally while repairing it, you could be sued into destitution. The Arkwright patent wars of the 1780s ruined dozens of textile manufacturers who merely installed machines that resembled his designs. Now imagine being the mechanic who actually built those copies. But patents were just the beginning. The guild system, though weakening, still had teeth. The worshipful company of clockmakers in London could legally seize tools and imprison anyone practicing horology without their approval. When clockmakers started adapting their precision skills to mechanical engineering, which many did, because timing mechanisms were crucial to early automation, they had to hide the transition. A clockmaker's shop openly building gear trains for textile machines. Guild inspectors would shut it down within days. Then there were the factory spies. This sounds paranoid until you realize that industrial espionage was the primary business model of the era. Matthew Bolton kept a list of suspected spies, and his correspondence mentions paying informants to identify which workshops were copying his engine designs. If your workshop got identified, you wouldn't just lose business. Bolton and Watt had connections to magistrates who could ensure your operation faced constant safety inspections and tax assessments until you closed. The most compelling reason for secrecy: restricted materials. High-quality iron and brass were controlled commodities. You couldn't just buy crucible steel. You needed accounts with authorized dealers who reported large purchases. So these workshops developed elaborate systems. A blacksmith would officially order materials for agricultural implements, then use them to cast cylinder heads for steam engines. The paperwork said plowshares. The forge made pistons. There's a documented case from 1794 Birmingham. A workshop was producing improved valve systems for Newcomen-style engines. Their innovation, a leather washer reinforced with brass rings, reduced steam loss by nearly 40%. But they sourced the brass by repairing church bells, essentially skimming material from legitimate commissions. When the church commission ended, so did their brass supply, and the workshop vanished from records entirely. Water power was another trigger for silence. Mill sites on good streams were licensed and monitored, but many small workshops used illicit water wheels, undersized, built into culverts or hidden behind false walls, tapping streams that officially had no mechanical users. These wheels powered lathes, drill presses, and grinding wheels. If caught, the workshop owner faced penalties for water theft, equipment seizure, and possible prosecution for fraud. Let me tell you about Thomas Holroyd, who never appears in any industrial history, but who probably revolutionized textile manufacturing more than a dozen famous inventors. Holroyd was a third-generation clockmaker in Halifax, Yorkshire. By day, he repaired timepieces. By night, literally from midnight to dawn, he worked on something else entirely. His workshop had a false wall. Behind it, a precision lathe, custom-built files, and an arrangement of brass gears that would have stunned any factory engineer. Holroyd specialized in one thing: improving the picker mechanism in flying shuttle looms. The standard pickers of the 1790s used leather straps that wore out every few weeks. Holroyd experimented with spring steel, clock springs, specifically, wound into tension systems that lasted months and hit with more consistent force. Mills started sending him broken pickers. He'd return them, repaired, but actually rebuilt with his spring system. No one asked questions, because the improvements were so significant that production increased 15%. Here's the human part. Holroyd trained his daughter, Elizabeth, starting when she was 9 years old. She became one of the most skilled file makers in northern England. Files were the era's precision tools, hand-cut with incredible accuracy, but no one outside the family knew. When Holroyd died in 1804, Elizabeth continued the work for another 30 years, signing all correspondence in her father's name. The Mills thought they were dealing with Thomas Holroyd's son. They were actually dealing with a woman who could measure tolerances by touch in near-total darkness. Or consider the Jebson brothers in Sheffield. They were officially listed as agricultural toolmakers, scythes mostly, but their real business was repairing and improving steam engine bearings. Early engines had catastrophic bearing failures because the bearing surfaces weren't true. The Jebsons developed a method using graphite-impregnated brass that they developed for clock pivots. This reduced friction dramatically. They worked in 2-hour shifts, never more than 3 people in the workshop at once, to avoid drawing attention. When a factory needed bearings, they'd receive a cryptic message: 3 scythes, curved pattern. That meant 3 bearings for a specific engine type. The Jebsons would produce them, package them inside actual scythe handles, hollow wooden shafts, and ship them as agricultural tools. The bearings arrived labeled as farm equipment. The emotional weight of this secrecy was crushing. William Jebson's diary, discovered in an attic in 1967, describes nightmares about being arrested, constant anxiety about shipments being inspected, and the agony of watching factory engineers receive credit for reliability improvements his bearings made possible. But more than that, he describes pride. "We know," he wrote in 1802, "that half the engines in Yorkshire run smooth because of us, and that's enough." There's also Sarah Kensington, a widow in Derby who inherited her husband's tool-making business in 1787. She couldn't legally operate it. Women couldn't hold business licenses in most trades, so she employed her teenage son as the official proprietor while she ran everything. Her specialty was producing better taps and dies for threading bolts. The official taps produced inconsistent threads that led to loose fittings and steam leaks. Kensington developed a hardening process using bone char that kept cutting edges sharper longer, producing far more uniform threads. She worked in total isolation, often going weeks without speaking to anyone but her son. When she died in 1811, her obituary mentioned only that she was a respectable widow of Derby. Her son sold the business immediately. He'd never learned the hardening technique, kept secret even from him. The knowledge vanished. Now we get to the engineering, and this is where it gets fascinating. Take bearing technology. The factory standard in 1790 was brass bushings pressed into cast iron housings, crude, but functional for low-speed applications. The problem came with higher speeds and heavier loads. Bearings would seize, shafts would score, and the entire machine would grind to a halt. The official solution was to use more lubrication and accept frequent replacements. The secret workshops found something better. They discovered that if you scored the interior of a bearing with shallow spiral grooves, essentially microscopic channels, the lubricant would distribute more evenly under pressure. This wasn't just better, it transformed reliability. A factory water frame that needed bearing replacement every 6 weeks could now run 6 months. Where did this knowledge come from? A millwright named Robert Chandler, who'd spent years maintaining waterwheel bearings, noticed that wooden bearings that had been gnawed by beetles, creating tiny channels, often outlasted smooth ones. He tested the principle on brass, then taught it to other mechanics. The innovation spread entirely through word of mouth and hands-on demonstration. No patents, no papers, no credit. Flywheel balancing was another breakthrough that happened in the shadows. Early flywheels were cast in crude molds, and their mass distribution was irregular. This caused vibration that destroyed mounts and cracked frames. Factory engineers tried to solve this by making frames heavier, reinforcing the structure to absorb the vibration. A clockmaker turned engineer named Josiah Webb saw the absurdity. He started drilling small holes in flywheels, carefully placed based on how the wheel spun when suspended from its center bore. By removing material from the heavy side, he could balance the wheel dynamically. This required precision measurement and an intuitive feel for rotational dynamics. Webb's method reduced vibration by up to 70%, which meant lighter frames, lower stress, and fewer catastrophic failures. He taught this technique to perhaps 20 craftsmen over 15 years, each sworn to secrecy because he feared patent litigation. The technique became standard practice in countless workshops before any engineer published a paper on dynamic balancing. Boiler technology saw similar underground innovation. The riveted seams on early boilers were death traps. The problem was cold riveting, hammering rivets into place at room temperature. The metal never fully conformed, leaving microscopic gaps that expanded under heat and pressure until the seam split explosively. A group of Sheffield metalworkers, most of them involved in armor restoration, oddly enough, developed hot riveting for boilers. They heated rivets to orange hot before setting them, which allowed the metal to flow slightly and seal better as it cooled and contracted. This seemed obvious in retrospect, but it required overcoming the fear that hot metal would weaken the joint. These craftsmen also pioneered double riveting patterns and taught other workshops to stagger seam lines so the weakest points never aligned. Factory engineers didn't adopt these practices until the 1820s, but secret workshops were using them by 1795. How many lives were saved by boilers that didn't explode? We'll never know, but probably thousands. Gear cutting deserves special attention. Early gears were cast, filed roughly to shape, and installed. The teeth were inconsistent, which created noise, vibration, and rapid wear. Precision gear cutting required equipment factories didn't have, specialized dividing engines and custom cutters. But clockmakers had been cutting gears with extraordinary precision for generations. When they transitioned to industrial work, they brought these skills. A workshop in Coventry developed a method using a modified clockmaker's lathe with an indexing head, a device that could rotate a gear blank through precise angles, allowing them to cut each tooth individually with jeweler's accuracy. These gears ran so much smoother than factory originals that mills would pay 3 times the price for them. The speed advantage was massive. A gear train with precision teeth lost perhaps 10% of power to friction, while factory gears lost 30% or more. That efficiency translated to real production increases: more cloth, faster pumping, longer machine life. Here's the beautiful irony. These workshops were trying to survive. They weren't trying to transform civilization. They just wanted to make enough money to eat and avoid prison. But in doing so, they solved problems that were bottlenecking the entire industrial revolution. Consider this reality. By 1800, Britain had thousands of machines that were technically operational but practically unreliable. A textile mill might have 20 power looms, but on any given day, 6 would be broken. The official manufacturers couldn't keep up with repairs, and their solutions were often inadequate because they designed machines but didn't run them daily. They didn't see the failure patterns. The secret workshops did. They saw every broken component, every wear pattern, every catastrophic failure. They accumulated knowledge that no single engineer possessed. When a workshop in Bolton figured out that leather belts lasted twice as long if you soaked them in tallow mixed with graphite, the knowledge spread through the underground network faster than any technical journal could have distributed it. These craftsmen became the unintentional research and development wing of early industry. Factories would install a new machine type. It would fail in predictable ways, and within months, secret workshops would have solutions, improvements that made the machines actually work as intended. The speed of knowledge transfer was remarkable. A breakthrough in bearing design in Manchester could be practiced in Sheffield within weeks, not through publications or formal training, but through traveling mechanics who carried techniques in their heads and hands. This was oral engineering tradition operating at industrial scale. Here's what's rarely acknowledged. Many famous improvements attributed to well-known engineers were actually developed in these workshops first. When a celebrated inventor patented an enhancement, he was often codifying something dozens of craftsmen had already been doing for years. The patent system recorded the formal claim, not the actual invention timeline. Take the slide valve improvement in steam engines, usually credited to innovations in the 1820s. But workshops were experimenting with improved valve designs in the 1790s. They didn't patent them because they couldn't afford the legal costs, because the designs infringed existing patents, or because they couldn't prove they'd invented anything new. So the work continued in silence until someone with resources and legal protection could claim the innovation officially. The economic impact was staggering. Historians estimate that early factories lost 30–40% of potential productivity to machine downtime and inefficiency. By 1815, that number had dropped to around 15–20% in regions with active secret workshop networks. That improvement, a doubling of effective productivity, had almost nothing to do with new inventions and everything to do with making existing machines work properly. These workshops also democratized mechanical knowledge. A young man couldn't afford a formal apprenticeship at a major factory, which required fees and connections. But he could work in a secret shop, learning by doing, paid in skills rather than formal credentials. This created a generation of highly competent craftsmen who understood machines intimately, but had no official standing. When factory engineers finally started systematizing these improvements, publishing them in technical journals, teaching them in mechanics institutes, they were often discovering what workshop craftsmen had known for decades. The formalization of mechanical engineering in the 1820s and 1830s was essentially the process of secret knowledge becoming public knowledge. The final, deepest irony: these craftsmen feared being erased from history, and they were. We know the names of perhaps 100 major industrialists and inventors from this era. We don't know the names of the thousands of workshop mechanics who made their machines actually function. Their fear came true. But their impact didn't vanish with their names. Every modern bearing, every balanced rotor, every precision gear carries the echo of techniques developed in those silent workshops. The industrial world we live in, reliable, efficient, standardized, was built as much in cellars and converted stables as in famous factories. They were trying to hide. Instead, they built the foundation of modern manufacturing. The machines that changed the world were invented in public and perfected in secret. That's the story no one tells, but it's the one that mattered most.